Yeah, if you read in the book or anywhere online, I mean, if you look up fundamental theorem of calculus here, you'll probably get lots of very formal stuff, but it's important to just understand the connection here of looking at area under curves. You can get it by subtracting, right? Now I went and closed that other thing here, but we can get it back quickly. So even if you have some crazy function, I really can't remember what this function is. It's some weird stuff I made up. Well, there it is. I wanted some kind of irregular sort of curve. Incidentally, if you have done Math 12 and you've done trig functions, the trig functions you do in grade 12 are all these nice, very regular periodic things. Any periodic function, even if it's sort of an irregular shape, you can model with trig functions as long as if you add a bunch of different ones together with different periods and different heights and stuff, you can get any kind of irregular shape like that with sine and cosine functions. That's your did you know fact for the day. If you want the area between here, if we want the area between there, I can get it by evaluating some antiderivative for this curve, evaluated for this value, for 6, and then subtract the same antiderivative evaluated for 2. Because what that's going to be doing is basically giving me that value, and then subtracting, or was I 2? Subtracting that value. The area underneath that curve between any two values, you get by subtracting the area. Subtracting the area all the way up to 6 minus this area here. And you can get that by using an antiderivative of this particular function, or whatever it happens to be. What's that? Well, it's hard to see geometrically here. Why the area under a curve is connected at all to the tangent. Like, if you go one way, if you have this function and look at its derivative, its rate of change, it's the tangent. If you go the other way, if you start with the function that represents the rate of change, if this is the rate of change, then the area underneath here represents the original, or the net change in the original function. That's the only hitch here, is it's the net change from there to there, right? This they call it the fundamental theorem of calculus is because it connects tangents of curves to areas under curves, which are two quite different things. You'll get it as we work through here. I don't want to get hung up on the really theoretical stuff at the beginning. It's better to kind of come back to that later. There is we're going to look at the other part at some point, come back to it. If you want to evaluate these, if you want the area between here and here, you might approximate it first, just by kind of looking and saying, counting squares here, 1, well, if I took this much here, and then let's say I took part of this and put it down there, I'd have 2, right? And maybe I don't quite have 3. It's going to be 2 point something. Okay? If you want to evaluate it exactly, what that area is, you use this integral evaluation formula. Okay? You subtract two different areas. You can use whatever antiderivative you want. You might as well use the simplest one. What's the simplest antiderivative of that? Simplest antiderivative of that? 1/3 x cubed, right? So let's put some words here first. Evaluated for x equals 2 minus, this is a lot of writing you're going to have to do here, 1/3 x cubed evaluated for x equals 0. But you should know by now, after all these years of math, that mathematicians are very lazy, and or they just like to make up symbols that makes it look like they're smart and nobody else knows what they're talking about. So you could abbreviate this as, put some square brackets around it, around this expression, 1/3 x cubed, and you can put, this is more like it, you put the 2 up there and the 0 down there. This is a shorthand for this. Okay?
Wow.
Nice. So don't write this out. I just made that up. I mean, I didn't make that up, but that's what this means.
Wow.
I didn't make it. I made up the abbreviation for evaluate. Yeah. I didn't make up this abbreviation, just so that's clear. You're lowering your standards if you're clapping for that. So then whatever that is here, I don't need to see all your work for that, but you're welcome to do this if you want. It probably would help to do this here, seeing it's the first time we wrote it out. 0 cubed. Well, 2 cubed and then divide by 3, so 8/3 minus 0, right? 0 cubed is 0. Well, connect it with the areas here, right? What's the area under the curve for here? Nothing, right? There's no area when you're at 0, right? So that should be 0. 8/3 minus 0, right? Or 8/3, right? 2 2/3, which is sort of along the lines of what it looks like it should be. 1, 2, if you count part of this one, and then most of another one. Now, there's some more definite integrals here to do. Think about the connection with what the graph would look like. If there's nothing in there, what is it? It's a 1, right? There's a 1 in there. What would a graph of 1 look like? It's a straight line at 1, right? There it is. If you want the area from 3 to 6, I'm pretty sure you can do that without even using that formula, right? What's the area?
How is it 0, Brandon?
Well, it's 1 times 3, right?
You got it use.
We know the area should be 3 here. If you're using this formula, what's an antiderivative of 1? X, right? So we want x evaluated for what values? From 6, and take away that evaluated for 3. So it's obviously 6 minus 3, or 3. Okay? You can do this one. This one's kind of ugly, right? It's okay. Well, you can do any of these things here, right? You can, as long as you have an antiderivative, you can evaluate it, right? So we want some antiderivative of that. What's an antiderivative of that? We got to go u is 2x plus 10, right? What's this then? This one's a pretty simple one, I think.
79.
U is 2. Du dx here is 2, right? So du is 2 dx. So dx is a half du. So the antiderivative of this, what's an antiderivative of that? If we want to do this, it turns into 1 half because of that. Square root of u du. What is that? This is like u to the 1 half, right? A half u to the half du. It's something like u to the 3 halves. We still need this here, and we need 2/3 here, right? So it's like 1/3 u to the 3 halves. So it's 1/3. I don't know why I put that second. That's kind of goofy. I got to put this stupid thing back in. You know what? It's not u to the half. What am I doing? Oh, it is. It is.
Correct.
Yeah, it is.
That is correct.
Square root of this to the 3rd, right? Sorry, I panicked for a second. It's that, right? So really you could go through and evaluate that, but what's the point, really? So -3, +3. (2x plus 10). This is painful. Why would a person have put this in here?
Don't you need the 1/3 there?
I need the 1/3 there. So you put the 3 in, and what do you have? Cube, like, it's probably easier to make it take the square root first, yeah? 4, it's 64/3. And you put -3 in there, what do you get? You get 4. 2 cubed 8 minus 8/3. So we have 56/3. That was a painful one. How far ahead of this do I tell you about how you can do it on your calculator? I can't remember. Not even in this section. Let's save that. Let's save that for another day. We're at 10 minutes here. Yeah. Can you do a few more of those really quickly for yourself while I stop?